All right, good afternoon, everyone. My name is Dana Waller. I am the Education Outreach and Diversity Specialist for the CPU2AL project. I would like to personally thank you all for joining this installment of the CPU2AL speaker series. Today, Dr. Gary Zank will be presenting the genesis of humanity's galactic adventure. Dr. Zank received his PhD in applied mathematics from the University of Natal in South Africa in 1987. Gary is an eminent scholar and a distinguished professor, director of the Center for Space, Plasma, and Aerodynamic Research, also known as EPSCoR, and he's the chair of the Department of Space Science at the University of Alabama in Huntsville. Go Chargers. Gary has received numerous honors and awards throughout his career. In 2017, he was named the University of Alabama Board of Trustees Trustee Professor, the first and only University of Alabama System faculty member to achieve this position. In part, this was in recognition of Dr. Zank being elected in 2016 as a member of the U.S. National Academy of Science, the only person in Alabama to be a member of this august body. Gary is dedicated to his research, which is clearly represented in his achievements over the years, and it categorizes him as a cutting-edge leader in the world of space, physics, and science altogether. Without further ado, Dr. Gary Zank.
Thank you so much, Dana. That's very kind of you. So I was going to talk about something that is both scientifically extremely interesting, but also appeals to the sort of our sense of humanity, and that is our very slowly stepping out of our solar and Earth environment, leaving that cradle, if you will, and entering into stellar space. And interstellar space, in a sense, is everything that is beyond the bubble that is created by the wind that is driven off the surface of the sun. So I wanted to talk to you a little bit today about our adventures, if you will, in reaching interstellar space. And I thought, what better way of beginning that than showing a movie? And so some of you, the older possibly members of the audience, might remember the book, The Hitchhiker's Guide to the Galaxy. What was so nice about The Hitchhiker's Guide to the Galaxy, there have been many, many books about science fiction stories and others about humanity's reaching and traveling through the galactic, through our galaxy, for example. But The Hitchhiker's Guide brought a refreshingly novel view of humanity's adventures in the galaxy. And I thought I'd begin by showing one of the opening scenes. The protagonist, Arthur Dent, a human, and his friend, Ford Prefect, named after the car that some of you may not remember. Ford Prefect was not a human. He was an alien from somewhere else visiting our small planet. And Arthur Dent was trying to prevent his council from bulldozing his home. Ford Prefect arrived, took him away from lying in the road where he was blocking the bulldozers, and dragged him into a local pub because there was a much larger event about to happen.
Warman, 6 pints of bitter and quickly. The world's about to end.
6 pints coming up.
Keep the change. You got about 10 minutes suspended.
It's 3 pints each at lunchtime.
You got 2 minutes. Drink up, drink up, drink up. Someone else. People of Earth, a round of drinks for everyone on me.
Oh, thank you, mate. You really think the world's going to end?
Yes.
Shouldn't we lie down or put a paper bag over our heads or something?
Well, if you like.
Will it help?
Not at all.
People of Earth, this is prosthetic Vogon Jeltz of the Galactic Hyperspace Planning Council. As you are probably aware, plans for the development of the outlying regions of the galaxy involve the building of a hyperspace express route through your star system. And your planet is one of those scheduled for demolition. There's no point acting all surprised about it. The plans and demolition orders have been on display at a local planning office in Alpha Centauri for 50 of your Earth years. If you can't be bothered taking interest in local affairs, and you end up on a pathetic bloody planet of no sympathy at all. Rises to the ground.
So with that, Ford Prefect and Arthur Dent managed to hitch a ride on the Voyager spacecraft, and that was the commencement of Arthur Dent's adventures in the interstellar medium. So, oops, I'm sorry. So a little while after that movie was made, or that BBC series was made, the principal investigator on the Voyager mission, now called the Voyager Interstellar mission, Ed Stone, had the following announcement to make. Oops, I'm not sure why it went past.
You are about to hear a discussion of a first in the history of exploration. The most distant human-made object, NASA's Voyager 1 spacecraft, is in interstellar space, the space between the stars.
So that was the Voyager 1 mission announcing that they had in fact confirmed that Voyager 1 had crossed a structure called the Heliopause, which I'll talk about in a few minutes, that they had crossed a structure called the Heliopause, leaving the bubble created by the wind generated by the hot solar corona expanding into the into interstellar space, creating a great big bubble, forming what is called the heliosphere. And so the heliosphere boundaries are the in a sense, is something called the heliopause. I'll show a picture of that later. And so then the Voyager 1 spacecraft found itself in the very local interstellar medium. The Voyager 1 spacecraft is one of two. There's the Voyager 1 and the Voyager 2 spacecraft. They were launched very, very close together, just I think maybe 15, 14 days apart in 1977. An extraordinarily long-lived mission, some 43, 44 years old now. In fact, I was still in high school in 1977. And so the Voyagers explored the outer planets of the solar system. And then after finishing with Uranus and Neptune, they then headed for the distant reaches of the heliosphere, hoping to in fact discover the boundaries and eventually reach interstellar space. And so a little bit about the Voyager missions. This is both spacecraft are more or less identical in structure. What you see over here is you have a roughly Beetle car-sized spacecraft. It has a very long boom to which is attached a magnetometer, something to measure the magnetic fields of the interplanetary and now the interstellar medium. It has a couple of instruments that are related to the measurement of cosmic rays, which turn out to be very important. This one instrument up here measures the so-called high energy cosmic rays, typically galactic cosmic rays, and something called anomalous cosmic rays. And down here you have a low energy cosmic ray instrument that measures energies that are hotter than thermal, but not highly relativistic. You have some photopolarimeters and infrared spectrometers. These were of interest for the planetary missions. Those are now switched off to conserve energy. And you have a very long, over here, 2 wires effectively that measure electric fields, and those measure also plasma waves as a result of that. So this is a very, very old system. Some of the electronics, incidentally, were in fact developed in Huntsville. This is powered by essentially radioisotope thermocoupled generators that are powered by plutonium. The plutonium has a short half-life, and so as a consequence of this, the Voyager 1 and the Voyager 2 spacecraft are rapidly running out of energy and may last no longer than another 5 years. So this entire system is based on very old heritage, 1970s heritage. And to give you a sense of the 1970s, I will talk briefly about its heritage in a few minutes. This little figure over here is supposed to show you the sort of galactic context of what the Voyager 1 and Voyager 2 missions are now exploring. The Voyager, the sun is this red dot at the center of the screen over here, and it's moving roughly in this direction relative to the other structures in the galaxy. These sort of higher density regions are where we are at currently. So this is in part called the local interstellar cloud, or the LIC. And it is a region that is a little denser and cooler than the region from which we've come, this region over here, which was probably created many, many millions of years ago by a supernova explosion that heated the gas up to approximately 1 million degrees. So the sun itself is slowly, its trajectory is basically orbiting the center of the galaxy. It has a very, very long period of about 33 million years in order to go around the galaxy once. And it oscillates in and out of the galactic plane, and it has a height of about 80 parsecs. To give you a sense of the scale, this is a logarithmic plot with the sun on the left, the various planets. You can see there's the Earth at 1 astronomical unit. And then you can see Jupiter, Saturn, and the outer Kuiper Belt objects, the other large gas planets. And you can see where Voyager 1 is and Voyager 2, and you can see that Voyager 1 is above the plane, the ecliptic plane associated with where the planets are orbiting, and Voyager 2 is below that. And so these 2 spacecraft are at quite similar distances. I'll give you exact numbers in a minute, but well above and well below this ecliptic plane, and so separated by an enormous distance over here. What you can see over here is Alpha Centauri. These are our nearest neighbors, our nearest star neighbors. It's a binary system. It's very similar, the nature of the stars. Alpha Centauri, they're G-class stars, which correspond to the sun. The sun itself is a G-class star. And so they're very similar in nature. What you can see is that the interstellar medium over here is essentially flowing on to the heliosphere. Here you've got something that we call a termination shock. It's a very large region across which the supersonic solar wind is rapidly decelerated to subsonic speeds. And then over here, you've got the so-called Heliopause, and that itself is the boundary between our solar neighborhood and the interstellar neighborhood. And you'll notice that there are things like the G cloud listed, and there's quite a bit of structure in the interstellar medium, so it's not completely featureless. To give you a sense of where the Voyager 1 and Voyager 2 missions are going and in the next, I don't know, million years or so, you can see that here's the Earth where they both originated from. It takes 8 minutes for light to get from the sun to the Earth. Voyager 1 is over here. I'll give you a better idea of the time that it takes for a radio signal to get from Voyager 1 to the Earth, or from the Earth to Voyager 1 or Voyager 2. But you can see that it takes on the order of about 19 light hours. In other words, it takes a beam of light 19 hours, or a radio wave 19 hours, to reach one of these spacecraft. Voyager 1 is going to go towards this system of stars over here. It'll pass by quite close to this so-called Gliese 445 system in about, and that's 1 point, roughly, you can see here, roughly 19 light years. So roughly 1 point, roughly 20 light years away from where the sun is. Voyager 2 will pass through the Andromeda system down further south, if you like. So Voyager 1 and Voyager 2, they've now escaped, in a sense, the boundaries of the solar system, of the heliosphere, and are destined to wander through interstellar space for the rest of the foreseeable future, billions of years, and unlikely to have anything happen to them terribly dramatic. Instead, what's likely to happen is that they will experience some gravitational perturbations as they pass by various stars, probably very small, but it will lead to a gradual wandering of the trajectories of the Voyager 1 and 2, and they will eventually just simply circle the center of the galaxy, just like the sun is doing. And that will continue into the foreseeable future. If anything happens to find and discover these spacecraft, both Voyager 1 and Voyager 2 contain a gold disk. This gold disk was designed in part by Carl Sagan, the late Carl Sagan, and it contains information about where the Earth is, about some of the of the animals, the sounds, the noises, some of the cultural information about the Earth. It includes, for example, the song Johnny Be Good. And so in some respects, this will be perhaps discovered by another civilization that lies outside in the distant galaxy. And in some respects, the gold disk and the information it contains will be our legacy to the galaxy. Unfortunately, while the gold disk sounds wonderful and very highbrow, the real legacy to the galaxy, it turns out, is in some respects the 1970s, which is a particularly depressing sort of legacy if for those older in the audience who remember the 1970s, perhaps with fondness or perhaps not. It's hard to be terribly fond of green shag carpet and this kind of plaid covering of a lounge suite. Their clothing fashions were pretty dreadful. This up on the left here is the jungle room in Elvis Presley's house in Memphis. And this on the right here is something that most people now have forgotten, but we used to use and collect music on 8-track devices, stereo 8-track devices. Rather remarkably, the Voyager 1 and 2 data storage system is essentially based on an 8-track type of device. It's essentially a piece of magnetic tape that just loops continuously, storing the data that is collected by the magnetometer or the cosmic ray instrument or the plasma wave instrument, or in the case of Voyager 2, the plasma instrument. It's collected on this, and then periodically all that information is sent down to the Earth. It takes, as I said, about 19 hours for the information to get back to the Earth, and then it's re-recorded. It's remarkable that after 43 years, this kind of tape is still working, still operative, still sending back very good data. I know for a fact that I used to have a tape machine, and after about 2 years, it no longer worked. So 43 years later, the Voyager spacecraft are continuing through the next to the sort of next region of their extended voyage, and they've passed these various boundaries. And this is just an example of what these boundaries look like. So the first boundary that they passed was the termination shock. This was the boundary that decelerated, the supersonic wind that blows out of the sun in a radial direction. The termination shock decelerates that supersonic flow to subsonic speeds. You then enter a sort of another boundary region called the inner heliosheath. That inner heliosheath is terminated. It ends at this heliopause that are described. And what happens here is that the solar flows are confined. The solar wind material is confined to this region between the heliopause and the termination shock. And it doesn't go out into this more distant interstellar medium. In this particular, in the interstellar medium, the flow flows onto this sort of obstacle and flows over and around the heliopause, and so it doesn't really mingle and mix with the solar wind flow. So the heliopause is the real boundary of the heliosphere, and so entering or crossing over the heliopause means that you've entered interstellar space. So just some things about Voyager 1 and 2, and I have to update this slide every time I give a presentation, because of course Voyager 1 is moving, Voyager 1 and Voyager 2 are moving at roughly 3 astronomical units a year. An astronomical unit is the distance from the sun to the Earth. 1 astronomical unit is that distance. And so the Voyager 1 and Voyager 2 spacecraft are moving at approximately 3 astronomical units per year. Very fast. And so Voyager 1 is on the order of 14.1 billion miles from the sun, which corresponds to about 152 astronomical units from the sun. Voyager 2 is at about, not as far, it's at about 11.7 billion miles, or 127 astronomical units from the sun. Just to put that in context, the distance to Pluto is only 3.6 billion miles. So much, much closer. And so the Voyager 1 and Voyager 2 are very much, more than 3 times further from the sun than Pluto is from the sun. And I mentioned that it now takes a radio signal from the Earth to reach the Voyager 1. It takes 21 hours, 5 minutes, and 17 seconds to reach Voyager 1 versus 17 hours, 35 minutes, and 6 seconds to reach Voyager 2. And then, as I indicated, Voyager 1 and Voyager 2 are vastly separated by about 10 billion miles. So on the 16th of December in 2004, Voyager 1 was the first spacecraft to cross the first of these boundaries, the termination shock, and Voyager 2 followed somewhat later on the 30th of August in 2007. And you can see in this little plot that, in fact, one was high up in the northern latitudes and the other was well down in the southern latitude. This is the kind of data that the Voyager 1 magnetometer returns. So these are measurements of the magnetic field. And if you stare at this, and if you've spent some time thinking about magnetic fields, this is the magnitude on this side over here, just before 2005. In other words, this period is just before the crossing of the termination shock. What you see is the magnetic field fluctuating quite strongly, but nonetheless is very low. It's only on the order of about 0.2 to 3 nanoteslas, a very small magnetic field, but it underwent a very significant jump at this red line shown over here. And that jump corresponded to the crossing of the termination shock by the Voyager 1 spacecraft. And that is where the termination shock acts to compress the flow and the magnetic field. And you can see that the magnetic field jumped quite significantly to become, instead of this 0.00, what did I say, 0.1? I should have said 0.03 or 0.5 magnetic field intensity. It is now about 0.12 or so nanoteslas and slowly decreases. And then something interesting starts to happen in this particular region over here. It turns out that we think the flow slowed down a little and it became a very complicated region. This over here, I don't want to discuss too much, but this is effectively telling you the orientation of the magnetic field. It flips back and forth because you're in the vicinity of something called the heliospheric current sheet. And in this region over here, the structure has changed quite markedly. And this was a hint that something interesting was about to happen. And indeed, at this point over here, right at the edge where this red dashed line is, we more or less did discover the second of the boundaries, and that second boundary was the heliopause, a very complicated event. And so what I've done is I've blown up in this figure over here. This is from Len Berlage and the magnetometer instrument team. What you see over here is the magnetic field as a function of time during the year 2012. And you can see late in 2012 that some very unusual magnetic field fluctuations began to occur. You would see a drop, and then you'd see this big rapid increase, rapid drop, another rapid increase, stays high, another rapid drop, and then another rapid increase. And then the magnetic field stayed more or less constant thereafter. And if you looked at the polarity, the direction of the magnetic field, what you tended to find was that it was pretty constant earlier on, and then it underwent this rapid change. If you looked at the energetic particles, particles that have an energy greater than 0.5 MeV per nucleon, what you found was that the number of particles that you saw per second was slowly decreasing, but very slowly. And then coincident with these big jumps in the magnetic field, you saw sudden rapid drops of the energetic particles. And then when you went through this final big jump in the magnetic field, what happened is a rapid and sustained drop in the energetic particles, and then this almost exponential fall off, and then almost nothing. And so as soon as people saw this, they concluded, aha, we must have crossed the heliopause, and we must have exited the heliosphere and entered interstellar space. And so that was the initial conclusion. But the puzzle was the following, is that the magnetic field, if you look at this particular plot over here, the magnetic field didn't really change direction. It looked as though it was basically the same direction as we had inside the heliopause. And so the question is, why should that happen? Why would you expect the interstellar magnetic field to somehow be oriented in a very similar way as the magnetic field inside the solar wind? And so this then led to a considerable debate in the Voyager community as to what exactly was happening. And so the conclusion was that perhaps we hadn't crossed the heliopause, perhaps we had not entered interstellar space. And so this structure was very imaginatively for a short time called the heliocliff, basically where all the particles suddenly disappeared as though they fell off a cliff. And so for a time, there was considerable puzzlement and disagreement about whether or not this was the heliopause or not. The reason we kind of expected it to be the heliopause was the jump in the magnetic field. Unfortunately, what we could not do was measure the plasma, because the plasma would have told us definitively whether or not we crossed the heliopause. And the reason the plasma would tell us definitively is because there would be a huge jump in the plasma number density in going from the inner heliosheath, this little green region over on the left, into the interstellar medium. And you see it's a very steep, very large increase in the plasma density. And the reason we could not see that was that the Voyager 1 plasma instrument had been broken after flying through the magnetosphere of Jupiter with its very high energy radiation. Those very energetic particles had basically destroyed the plasma instrument. And so we could not make measurements of the plasma density. In any event, were we able to make measurements of the plasma density, we would have seen, in fact, that this very high jump in magnetic if this was coincident with the magnetic jump, we would have then concluded this is definitely the heliopause, but we did not see that. So sometimes science proceeds by very fortuitous events, and not surprisingly, something very fortuitous just happened to occur. I mentioned that there's a plasma wave instrument on the Voyager 1 spacecraft. And what that plasma wave instrument does is it measures the frequency of oscillations in the background plasma. And so in and or around early part of 2013, a very strong burst of plasma oscillations were seen. This was at first it was thought that this was the first such set of oscillations that had been seen since before Voyager 1 crossed the heliospheric termination shock. And what is interesting about the plasma oscillations is that you can use the frequency of those oscillations. This is the frequency plotted on the left. You can use the frequency of those oscillations to infer what the number density, how many particles per cubic centimeter there might be where these plasma oscillations are measured. And so I was on the way to the swimming pool, I think must have been in late May, when I got a call from the PI of the plasma wave instrument, Don Gurnett, who said to me, "Gary, what would you say to me if I told you that the plasma wave instrument had just measured a number density of about 0.08 particles per cubic centimeter?" And so my immediate response to him was, well, I would say that you're measuring oscillations in the interstellar medium. And he said, good, that's what I wanted to hear. And he said, but he would not tell me why he was interested in this. So, however, it shortly came out then, shortly after that in fact, this was the plasma measurement that had been made in April, May of 2013, after that heliocliff event. And in fact, what was further seen when they went back and looked in the data, remember this data gets sort of deposited, once the magnetic tape gets filled, so you only tend to see these things a little while later. In fact, there were more oscillatory events that were seen at an earlier period, and so you can see that there was a ramp corresponding to that very steep climb into the interstellar medium across the heliopause. And so, in fact, this then was confirmation that the Voyager 1 spacecraft had crossed that huge plasma density increase into the interstellar medium and, in fact, was now in interstellar space. And so, looking at this then from the perspective of May or thereabouts, June, much later, we can put the whole story together. What Gurnett saw much later was, in fact, a great big shock wave that had passed by. It was responsible for setting up those plasma oscillations that were measured by the Voyager 1 plasma wave instrument. And we were able then to infer the number density from that. And you can see that the magnetic field, in fact, increased a little as a result of that shock wave. That shock wave, incidentally, was generated by the sun, probably on the order of about 400 or thereabouts days previously, and had then propagated through the supersonic solar wind, collided with the heliospheric termination shock, propagated on through the inner heliosheath, collided with the heliopause, which is this over here, and then was partially reflected and partially transmitted, and then propagated into the interstellar medium and produced those plasma oscillations that allowed us to determine that, in fact, the number density was close to 0.1 particles per cubic centimeter, more or less what we expected for the interstellar medium. So that was a really remarkable set of results, and the conclusion was Voyager 1 was now in the interstellar medium. And in the meantime, these were the galactic cosmic rays, the very high energy particles that are much greater than 70 MeV per nucleon. And you can see now that we see this continuous bath of galactic cosmic rays that surround our heliosphere and slowly enter and are modulated by the supersonic solar wind. So that was the discovery of, first of all, the Heliopause, very exciting, very dramatic event. And it was also the discovery of the first shock wave in the interstellar medium, at least direct in situ measurement of a shock wave in the interstellar medium. And these kinds of, and the excitation of plasma oscillations as I described. And it also indicated that, in fact, the heliosphere in its small way was able to affect, mediate, and modify the very local interstellar medium. So these were some really dramatic discoveries made by Voyager just as it entered the very local interstellar medium. Voyager 2, coming along much later, was eventually crossed the heliospheric, the Heliopause 2 on the 12th of May in 2018, and in fact saw structures that were in many respects quite similar. You can see, for example, down in this bottom figure that there is a fairly dramatic drop-off of the same sort of energetic but not very energetic particles, these 0.5 MeV per nucleon ions. You can see that there's a drop and a slow decay. It's a little different in terms of the drop. You can see that the very energetic, the galactic cosmic rays, all asymptote towards more or less the same same upwind value. But there are differences in detail about how the transmission process across the Heliopause occurs, both for incoming galactic cosmic rays and outgoing lower energy, possibly anomalous cosmic rays. So lots to discover and lots to investigate. So what is the basic physics underlying a lot of this? Well, one can spend a great deal of time trying to understand the basic physics, but the physics in large part is controlled by a combination of neutral gas, neutral hydrogen, and plasma, charged particles, electrons, protons, sometimes charged helium, and so forth. And it's this combination of it's this interaction of the plasma and the neutral hydrogen, these hydrogen atoms, that determines in many respects the basic physics of what we've been investigating for the past 20 odd years. And so you can imagine, just in a cartoon sense, that this is the solar wind, the heliosphere, this is maybe the Heliopause, this is this radial solar wind that's expanding from the sun. The sun is moving through the interstellar plasma, or in a sense like this perhaps. And surrounding the heliosphere is this mixed sort of gas of neutral hydrogen atoms, and charged plasma. And in fact, there's much more of the neutral hydrogen than there is of the charged plasma. The number density is of the plasma, as I showed just a few minutes ago, is on the order of about 0.1 particles per cubic centimeter, whereas the neutral gas number density is maybe double that, possibly 0.2 or even larger. And the process by which these two gases, the charged gas and the neutral gas, are coupled is via a process called charge exchange. And charge exchange is a relatively simple process. It's essentially a collision between the green charged proton and the blue neutral hydrogen atom. And so if a hydrogen atom comes close enough to a green proton, or just to a proton, which is green on the picture, if it comes close enough, the proton can sort of, in effect, snatch the electron that surrounds the neutral hydrogen, can snatch the electron and take it for itself. When it does that, the solar wind ion is no longer charged because it's a proton, and so add an electron to it and it becomes neutral, and so then I produce a new neutral atom. Remember, the proton is gyrating around the magnetic field, it's charged, and so as soon as it becomes neutralized, it leaves the magnetic field and travels in a ballistic sense in a more or less straight line at the time it was created. What happens to the neutral hydrogen that lost its electron? Well, that now suddenly becomes a charged particle, a charged proton. And so it immediately begins to gyrate around the magnetic field, as illustrated on the right. And because it was typically moving at a speed that may be different from the speed of the plasma, it also sees a motional electric field, the U cross B motional electric field. And as a result of that electric field, it gets accelerated up until it co-moves with the background plasma, at least in the perpendicular sense. And so it gains energy. And so the plasma loses some energy in accelerating the so-called pickup ion that has just been created. And so the plasma loses some energy and momentum, the pickup ion gains energy and momentum. And so this process can happen in the interstellar medium. In the interstellar medium, the gas, the neutral hydrogen gas, and the plasma tend to be co-moving. And so there is no relative velocity between the two. And so when charge exchange occurs, it's more akin to a relabeling process than anything else. However, in the supersonic solar wind, where you have the solar wind moving at perhaps 400 or 700 kilometers per second, and the neutral gas is just drifting inwards at maybe 20 kilometers per second in the opposite direction, well, then the newly created pickup ion will see this very large difference in velocity and will see a large gain in energy because of the emotional electric field accelerating it up so that it co-moves at that same speed. And so in the supersonic solar wind, I typically produce an energetic ion called a pickup ion, which may have energies on the order of 1 keV. So how do you describe this kind of system? Well, for those in the audience who may have a slight mathematical bent, it's a very interesting and very complicated process to describe this and model this in a quantitative way. And so what one needs to do is you need to model the plasma, but at the same time, you need to model the neutral distribution. The plasma you can write down, at least in a sort of low frequency limit, using what are called the magnetohydrodynamic equations, where things like the density and the velocity and the pressure correspond to the plasma. And you have source terms in the momentum and energy equations corresponding to the gain and or loss of momentum and energy due to the pickup ion process that I just described. Remember, when the newly created pickup ion can be accelerated in the electric field induced by the motion of the flowing plasma, that's going to change the momentum of the plasma and also the energy of the plasma. And so you're going to have that effect needs to be incorporated. And so you have these kinds of source terms due to that creation process of pickup ions. The neutrals, on the other hand, you gain and lose neutrals as a result of the charge exchange interaction, and one of the complications about the neutral gas is that the scale length over which the charge exchange occurs can be quite large. And so in the interstellar medium, the scale length for charge exchange is on the order of 50 to 100 astronomical units, whereas the scale length of the boundary regions is actually less than that. And it's even, and the charge exchange mean free path in some of the boundary regions is even longer than 100 astronomical units because of the very low number density or the hot plasma. And so the boundary regions are on scales smaller than the charge exchange mean free path. And so that means that you have to be extremely careful in how you treat the modeling of the neutral gas. And the safest way to do that is to, in fact, solve what is called the Boltzmann collisional form of the Boltzmann transport equation, which is written down at the bottom. And you'll notice that it's a very, very complicated equation because it has integrals that are related to the distribution of the hydrogen and integrals that are related to the distribution function of the protons. And so this set of collisional integrals on the right-hand side has to be solved consistently while you're solving the magnetohydrodynamic equations. And so that has been an ongoing and subject of investigation. Started out in the mid-1970s to some extent. It was recognized in the mid-1990s that this coupling was absolutely critical to the problem. That's in fact when I got involved in this problem. And so there were two different ways devised for treating this kind of very complicated coupling between the two elements. I won't go through that. This is just a very simple way of actually solving that integral differential equation that I described purely on the basis of a kind of hand-waving argument. And the idea here, it's quite simple. You've got the supersonic solar wind. It moves out at 400 kilometers per second. It's dominated by bulk motion. It goes through the termination shock. This region beyond the termination shock is instead dominated by very hot plasma that is created as a result of crossing the termination shock. Here you've got the heliopause through which prevents this plasma mixing with the plasma out in the interstellar medium. And here you've basically got plasma and neutral gas that's sort of equilibrated. And so what you'll find is that the neutral plasma just flows in. It crosses possibly a bow shock that is in front of the entire system over here, and it causes the plasma to divert, cool, and divert, be heated slightly, and be compressed slightly. Rather weak because the bow shock's rather weak. If I go on and then ask myself, well, what happens if I have a neutral hydrogen atom coming in here? It crosses this electromagnetic barrier without caring about it in the least, but at some point it may experience a charge exchange collision. And when it experiences that charge exchange collision, what is it doing? It's exchanging, it changes, it swaps part. Basically, the neutral hydrogen atom becomes a pickup ion, as I described, and that's this little dashed line over there. But the new neutral atom that I've created corresponds to the diverted, decelerated, and heated plasma proton, and so that proton becomes a neutral, and it too is decelerated, diverted, and hotter, and so that then produces a trajectory that looks like that. And so what's going to happen in this region is you're going to see a great big pileup of neutral hydrogen. And I'm going to stop there. There's lots of other interesting arrows, but I'm going to stop there. One of the predictions then that emerged from this is that you get a pileup of neutral hydrogen. So moving on very quickly and ignoring everything else in these arrows, which, as I said, is a graphical way of interpreting the solution of the integral differential equation. One can, in fact, then solve that equation. And as I said, one of the predictions is that you produce a wall of heated hydrogen in the region between this so-called bow shock and the heliopause. And here's a simple, very old graphic that shows this in a very attractive way. So this is the plasma at the top. This is the neutral hydrogen at the bottom. You can see the hot plasma, heliopause, and coincident with that, you see in this region, a region of high density neutral hydrogen. So that is a very interesting prediction that emerged in the late 1990s as a result of these models. At the same time that was happening, two colleagues of mine, Brian Wood and Jeff Linsky, were looking at the nearby star Alpha Centauri, which I showed you way back at the beginning of the presentation. They were using Hubble Goddard high-resolution spectrograph observations, and what they were looking at is something called Lyman alpha absorption between the Earth, Hubble, and Alpha Cen. And they were trying to calculate how much of the Lyman alpha light emitted from the Alpha Cen star was in fact absorbed on its propagation path from Alpha Cen to Hubble Space Telescope. And so what they observed was this little this sort of jagged line over here. if there had been no absorption, they would have observed. I'm sorry. If there had been no absorption on the way, they would observe this this particular line. However, there's absorption, and so this then eats into this side of the spectrum that they observed, and so they saw then this missing region of light. And so they concluded that, in fact, it was absorbed because there was neutral gas in between Alpha Centauri and us. The puzzle, however, was that they were expecting to see a slightly different line, that dotted line over there. And the reason they were expecting to see that is because they had a very good idea of how much neutral gas was present in the interstellar medium. But what they saw was this extra absorption. And so to explain that extra absorption, they said, well, there must be a very small cloud embedded within this larger cloud of neutral gas that was hotter, moving at a different speed, and had a higher density, and happened then to absorb this extra light. And so that absorption, which is kind of illustrated over here. Here's the star, there's the light, there's this region, there's the absorption, there's what was expected, there's this extra absorption that could not be explained. And the way that it can be explained is that, in fact, there's a hydrogen wall that happens to be there, which has a slightly higher density, a higher temperature, and a different velocity vector from the cloud that's in between Alpha Centauri and the sun. And so that turned out to be the first discovery. It turned out that a couple of postdocs working with me, we were able to show explicitly that, in fact, that dashed dotted line over there could, in fact, account for the absorption when you included this hydrogen wall that was discovered. So that was very exciting. So then there became a whole industry devoted to trying to understand the parameters of different winds, different directions, and this was used as a way to probe the interstellar medium. These models have become vastly more sophisticated, and this is a very nice model that and graphic that has been that was developed by some colleagues of mine, Jacob Heliopause, Anthony De Stefano, and others, showing the hydrogen wall, the plasma structure, and so forth. So besides looking at the sun and hydrogen walls, it turned out that this work was able also to discover the existence of corresponding hydrogen walls around other stars, such as Alpha Centauri. And that comes about from looking at the other side of that absorption feature. So I'm not going to go through the details of that. I will just point out that Alpha Centauri and Proxima Centauri are very nicely co-located in the sky. These are our closest stellar neighbors. Alpha Centauri is a G-class star, just like the sun. Proxima Centauri is a white dwarf. It's become very interesting in terms of exoplanets. If you take the Hubble telescope and you look at Proxima Centauri and you look at Alpha Centauri, you're basically looking through the same interstellar cloud of neutral hydrogen. And so if you see differences in the absorption characteristics when you look at Proxima Centauri versus Alpha Centauri, you can then conclude that the differences are due to the star and its interaction with its local interstellar environment. And so what we did was we explored that. We looked at the so-called blue side. And what we discovered is that Alpha Centauri had no absorption component. Proxima Centauri had no absorption component, but Alpha Centauri did. And as a consequence, that allowed us to discover both another hydrogen wall around another star and also to discover a companion wind, very like the wind that comes from our sun. So this was the first discovery of a stellar wind from a G-class star. So that was very exciting. So the overarching conclusion that I want to leave you with is that we're beginning to understand the basic physics underlying the interaction of the solar wind with the interstellar medium. Voyager 1 and 2 are undergoing a perhaps billions of years long journey around the center of the galaxy. We will lose contact with them. Perhaps they will be discovered by another civilization, who knows? But in some rather sad sense, they're our legacy to the galaxy. If nothing else, hopefully there will be another spacecraft with a more up-to-date set of instrumentation and perhaps a more up-to-date gold record. In the meantime, however, we've discovered the importance of interstellar processes in shaping our solar wind and the boundaries of the heliosphere. Now that the Voyager 1 and 2 spacecraft are in the very local interstellar medium, we're beginning to learn how important our heliosphere and heliospheric processes are in determining the characteristics of the interstellar medium. I should add, in conclusion, that this field is developed like any other field of science, with its disagreements and controversies and exciting personality conflicts. Even though we're all looking at the same data, the interpretations and the opinions of people can differ significantly from scientist to scientist. And I thought I'd close the talk with the following real-life example of how science is really done. So this is my last slide, and I hope you enjoy.
I figure 75% to you, Panma, and 25% divided between the 5 of us. Yida, Crowbar, myself, Tom, and the baby. That makes 5% for each one of us.
Billy, you're cheating yourself. If there's 25% divided among the 5 of you, that's 14% apiece.
Oh, no, listen, Pa. I wouldn't cheat you. You know I wouldn't. Now, look here. I'll show you. Let me rub this out here. And now, 25 divided by 5 is 5. You see, 5 won't go into 2, will it? No. But 5 goes into 25 5 times, you see?
No, you're wrong, Billy. Now, I'm a pretty good mathematician. Now, 5 into 25... 5 won't go into 2, will it?
No.
But 5 goes into 5 once. Now, we didn't use the 2 before, so we'll bring it down here. Now, 5 into 20 goes 4 times. There you are. 5 into 25, 14.
No, look, Pa. Let me prove it to you now by multiplication. 5 times 5. 5 times 5 is 25.
Really, I'm surprised you're learning.
Huh?
I'm surprised that you're learning. Now I'll show you. 5 times 14 is 25. 5 times 4 is 20. 5 times 1 is 5. 25. That's it.
No, look, Ma. Look, you're wrong there because I'll prove it to you. We'll put down 5 14s here. 14. There. Now I'll prove to you by addition that 5 14s is not 25. 4, 8, 12, 16, 20.
21, 22, 23, 24, 25. There you are. Better brush up, Billy. I don't want to see you boys cheated.
All right, that's it. Thanks very much, everyone. Enjoy the rest of your day. All right, Dana, over to you. Oops, I'm not sure I can hear you if you're speaking.
Thank you, Gary. Apologize. Thank you so much, everyone, for joining today's installment of the speaker series. Thank you, Dr. Zank, for this compelling lecture that you gave us. It was quite interesting. I really enjoyed it. I would like to remind everyone that's on this live stream to subscribe to our CPU2AL YouTube channel. More content will be coming, lectures, student presentations, and just all around good science knowledge, especially focused on low temperature plasma. Again, thank you all for joining and have a great day.
Thank you, Dana. Bye-bye, everyone.